welcome. Okay, so let's continue with our problems. So the last problem we did was 14, right? Now let me remind you some basic facts we need for this seminar. Well, let's remember some theory. So first, the axioms in strings. So the axiom number 1 is that for any symbol of the alphabet A and for any string S, the empty string cannot be represented as S column X column S. Okay, this is the first axiom. And the second one is that for all symbols X and Y and for all strings S and T, the string X column S is equal to the string Y column T if and only if the heads are equal and their tails are equal. So if and only if X is equal to Y and S is equal to T. So these are the two basic axioms we need for strings. Okay. Now let me remind you also the append function. So we have the append function, and we did not define what the append function is. We defined how. So we gave a recursive definition of this append function, right? So and we say that for all X and for all T and S, so for all symbol X and for all strings T and S, the app of a string, of an empty string, and T is going to be T, right? And the app of X column S and T is going to be X column, the app of S and T. So this is the recursive definition of the append function, right? And in class you proved the following lemma. So it was lemma, let me call it lemma 1. You proved that for all S and for all T and for all R, so these are strings, so these are strings, belongs to SA, the set of all the strings in the alphabet A, holds that the app of S app TR is equal to the app of the app of ST and R. So that we can change. So this here, the function app is be applying to T and R, but we can change it just to be applying to S and T, and the result is going to be the same. So we are going to obtain the same result for this case. And so I think this is, by now this is enough for start with for problem 15. Well, I think you, so for problem 15, let me write it, but anyway, so 15 said that for all S and T and R, so for all S, T and R strings in some alphabet A, if the app of ST is equal to the app of SR, then T is equal to R. So these two, so that if we have the app of ST and this is equal to some app of SR, since S is the same here, then T is going to be the same to R, okay, the same string. You proved that in class, I think, in the lecture, so this, I can prove it again, but I don't know if I need to, but because I believe that you did that in your class, and not yesterday, but the last week. So, right? Do you remember? What, sorry? Uh-huh. Yeah, but did you do this in class? Yes. Do you don't remember? Anybody from home? Does anybody remember? No? Okay. Well, let's do it again then. So. Of course, we have to prove this by induction. Of course, yes. So we have to prove this by induction. It means that we have to consider two cases, right? So the basis step is the following, that we consider. So we have here three different strings, right? S, T, and R. So we are not going to, I mean, we should somehow prove by induction on each of them, of each of these strings. So we should prove by induction that this holds for any S, for any T, and for any R, right? So we should do this 3 times. But we can just say the following. We can just take T and R arbitrary, any, and then we are going to apply induction to S. So let T and R be arbitrary. So T and R can be any strings you want, okay? And then we are going to apply induction just on S, okay? And at the end, since we obtained that this is going to be true for S, and T and R are arbitrary, then this is true for every S, T, and R. Okay? So first, of course, we take S, the empty string, and we see what happens. So then we obtain that the app of empty string and T should be equal to the app of the empty string and R. And we see, so we have the app of empty string and T and the app of empty string and R. And by definition, from here, we see that this is equal to T and this is equal to R. So T is equal to R, and for the base step, the statement holds. Okay. Now, the inductive step, inductive or induction? Inductive, yes, inductive step. So here we took S empty string. Now here we have to take S any string non-empty. So what does it mean that S is any string non-empty? Is that we can represent this X as X column S prime, right? If S is non-empty, then there exists some S prime and X that we can express this string in this way. Okay, and now we have to apply all this for this one. So then, what do we obtain? We obtain the following. The app of x column S prime and t should be equal to the app of the x column x S prime R. Okay. And yes, we have this. Now, what do we know from here? We can look at that definition. Yes, we can take this x out. Then this is going to be equal, this is going to be equal, this is going to be equal to x column, the app of S prime t, and this is going to be equal to the x column of the app of S prime R. Okay, and then this has to be, these two things has to be equal. But when is this true? This is true if and only if. So this is true if and only if what? We have to see to the definition. So we have that two strings are equal if and only if their heads and their tails are the same. Okay? So this is if and only if x is equal to x is equal to x. That's true. But what about this? So if app S prime t is equal to the app of S prime R. Okay, so is this true or false? By the induction hypothesis, this is true because so here we prove for the empty string, and here we say that for any S prime, this condition, so this going to be, I don't know, let's call it phi, right? Phi, yes. That phi holds for any S prime, and then we want to see if this holds for this new string, and then we obtain this, and by the let's write them. Yeah. Then by the induction hypothesis, this is true. This is true. Okay. So what does it mean that this is true? That t is equal to R. Then this holds. So we obtain that for the base step this holds, and for the inductive step this holds. Then we've proved everything. Okay. So I wanted to remind you. I don't know your lecturer how he does that, but in every proof, every time I try to resolve something, I start with this opened rectangle here, and I finish with this kind of rectangle. So look at this. This is that I start with the proof and I finish it. Okay. I'm sure that you already noticed that, but anyway, and that's it. So we finished with number 15 that anyway you already did on your lecture, because I know that. Okay. Okay. Now 16. Number 16. This is the last one, I believe. Yes. So we have A and B. So we for this we need to define a new function, the reverse function. So let me write that here. So can you see? Yes. So the reverse function. How are we going to define that? Well, first one we're here. So let's say that for all x So for all symbol in A and for all strings S, the reverse function of an empty string is the empty string, and the reverse function of X column S is equal to app of the reverse function of S and X. So this is the recursive definition of the reverse function, but what is it? So for example, so let's write here an example. What would be the reverse of so we have a string here, 3 to 1, right? And we are applying the reverse function. So what string do we obtain here? 1, 2, and 3, right? So we are changing the position of each of the of each of the elements of the string. Okay, so the first is going to be the last, and so on. Okay, and we can define that function just with these two recursive definitions. Okay, so the reverse function of an empty string is an empty string, and if we have X column S, then we obtain this, the app of the reverse of S and X. Okay, now we know this, and we will need this also, so do not forget about this lemma that you proved in your lecture. So we have to prove the following. So this is number 16. So for all S and for all T strings, right, holds the following, that the reverse function of the app of ST is equal to the app of the reverse function of T and the reverse function of S. So we need to prove this. We have the reverse function, the app function, and the reverse function. So it is true or false? So every time we want to check something, for example, if we want to check this, we can say yes, let's do it by induction. But what if this is not true? You know, so it's good if this is the first time you see something, you have to check just with some example, with some simple example. If you see that it holds for this simple example, so it maybe so it should be hold. It should hold for any example. Okay. So I don't know. Let's take the let's S be 1, 2, 3, and let T be 4, 5, and 6, right? So what is going to be the app of S and T? So the app of S and T is going to be what? Huh? Yes. No, Y3. No, just the app of S and T, not the reverse, just the app. So it's going to be 1, 2, 3, 4, 5, and 6. Yes. And the reverse of this is going to be 6, 5, 4, 3, 2, and 1. Now let's check if this holds for in this case. So what's the reverse of T? 6, 6, 5, and 4, right? and the reverse of S is 1. And so the app of the reverse of S and T, of T and S, T, the reverse of S is going to be 6, 5, 4, 3, 2, 1. So,
the reverse solution works to statements also.
Just one. Oh, a statement, you mean strings?
No, I mean, for example, the board is white. I can use a reverse function just to change the statement, or it's supposed to.
No, the reverse, look, the reverse function is a function defined on strings.
Just?
Yes, just on strings, okay? Everything we've studied after we start with the strings is apply on strings, okay? Just strings. So they are the same, right? So we think that this should be true. Now let's prove it then. Okay. So what do we need to do in this case? So we need to prove by induction. On what? So we have how many strings here? 2 strings, right? S and T. So how are we going to apply induction? On what string? What do we need to say? So, yes, the same that we did here. So we said let T be arbitrary. So any string, and then we are going to apply induction on S, okay, on the string S. So the base step is what? What do we need to consider now? Yes, so that S is the empty string. Then, so we consider that S is an empty string. So we need to put empty string here, right? So the reverse of app of S and T equal, so yes, so this is equal to what? So S is empty, right? Empty string. This is equal to what? So what is this equals to? We have the app of the empty string and T. What do we know about this? This is T, yes? Why? Because of the definition of the app function, okay? Empty string T will be T. So we have that this is the rep of T. Okay, and now what do we need to show? We need to show that this, so that this is equal to this. But we obtained this. So what do we need to do here? In this case, what is S? In this case, empty string. So what will be the app of the reverse of T and the reverse of the empty string? It will be the reverse of T, right? So this is equal to the app of the reverse of T and the reverse. Well, Actually, we should do the following. So, yes, the reverse of the reverse of the empty. So we obtain that this is equal to this for S empty string, so that the condition holds. Okay, so we check this. We check the base step. Now we need to check the inductive step. So don't forget to put your plus on YouTube or Zoom. I don't know right now. Any of you is going to discuss your homework today? No? You're going to, okay, good. So, okay, I think that about that. So we are meeting tomorrow in Zoom with, I think nobody sent me anything new. So with all of you who sent your homework the last week, we're going to meet tomorrow, and I will give to each of you about, I don't know, 20 minutes, 30 minutes maximum, because there's a lot of you. So the last time I spent just 1.5 hours talking with one person, so it's a lot of time. So let's see how we do. It would be much better if you all come, but okay. So the inductive step, right? So we already did this for the empty string. Now what is going to be equal S? Yes, so this is going to be X column S prime. So we are assuming that this condition holds for S prime. Okay? For S prime, this is true. Now we need to show that for S, this is going to be true as well. And then we need to do the same. So we need to put this into this. All right? So the rep of app st, yes, app st, s app rep of app s. So this is equal to what? What is it equal to? So we have the app of X column, S prime, and T. So we can take X out, right? So this is the reverse of X column, app of X, S prime, T. So now what? So what is this equals to? How can we find that? So we need to find what value do we need to put here if we are looking for the reverse function of something. So we have the reverse function of X column some string. So we need to look at the definition, right? So what's the reverse function of x column some string? Yes, and then by definition, this is equal to the app of the reverse of what? Of S, so of this, of the app S prime t and x. So by definition, this is equal to this. Good. Now, what can we say here? Look at this. The reverse of the app of S prime t. What are we trying to prove? The reverse of the app of ST, right? X is a string with X. So this is an element of where here you mean? Okay, let me write this again. App of the reverse of what? The reverse of this, of the app of S prime t and the string x. Yes? Now, what is this equal to? So this is what, so we are trying to prove this for any string S. And here, we assume that this is true for S prime. And we have here S prime. So this is equal to what? So equal to what? So, okay, let me repeat this. So, look, we have this, look at this, the reverse function of app S prime t. This is the same, almost the same as the reverse function of app st, right? What's the difference? We have here S, we have here S prime. We are trying to prove this by saying that this holds for S prime. So this is equal to what? No? Yeah, we have to put this there, but with the S prime, right? Because we know that this is true for S prime. So we can just put this there. So this is going to be equal to the app of okay, so the reverse of x, that is just x, right? Wait, so this is app of, okay, the reverse of app, this is going to be app, reverse is going to app, reverse of, in this case, t is t, yes, and s is app of s prime t, app of s prime t. So the app of this and x. So the app of this and this. Okay? Again, we put this here. So we know that this is equal to this by the, okay, by induction hypothesis. So now we have that the app of two strings and other string. So we have three strings here: rep t, app s prime t, and x. And we have that the app of these two strings and the app of these two strings. So what can you see from here that can be useful for us? So look, we know that if we have the app here in the app, okay. So we have three strings S, T, and R, and if we have the app here, or if we have the app here, so if we change the string in which we are applying the app function, so in this case we are applying app to T and R, and in this case to S and T, we are going to obtain the same. Okay, so what can we do here? We can change this. We can change this app. This app is applying to this and this. Now we can put this app applying just for this one and this one. So this is going to be equal by lemma. So by lemma 1, this lemma that you proved in your lecture, to what? To the app of the reverse of T and the app of the app of S prime T and X, the string X. Right? Clear? Yes? Yeah? No? If there's some question, just No. This we wrote because of the induction hypothesis. Because of the. So look, we had this. So this is going to be equal to this. Yeah, look. We have rep and app, and we have rep and app here, right? So we can change this rep and app. We can change it for app, rep, and rep. That's what we did. So for app, rep, and yeah, you're right. By the way, there's something. So for so this should be rep the app. This should be then the rep of app. Yes, app, rep app. Let me rewrite this. Okay, so let's write this again here. So this is going to be the app of the rep app S and T. No, it was it was correct. Okay, so it was okay, but so we have to put the, yes, we have to put then the app of the app of ref of t and the ref of s prime, right? Yes? No? Ah, okay. Yeah, I just, so what was the question? You understand? Okay. Yeah. Okay. Then it's okay. So let me rewrite this. Yes, it was okay. So the app of this and this and x. And now this is equal again. This is equal by lemma 1. By this lemma, this is equal to the app of rep t, the app of rep s prime and x. Yes, good. Now, I think we can erase this. Now, what is this equals to? What is this equal to? What can you see that we can change here? What about this one, this part? What is this equal to? So what about the definition of the reverse of x column s? This is the app of the reverse of s x. The app of the reverse of s prime and x. So we can put this here. So, So by definition, he is going to be equal to the app of the reverse of t and what? And the reverse function of what? So we have s prime, x, s, so x column s prime. Right? Now, what do you think? So we just change this by definition for this. So this by definition is equal to this, to the reverse function of x column s. So we change it, and we obtained, well, this is going to be the same, and we change just this part. Yeah, now, equal, this is going to be equal here. So what did we obtain? The app of what? Of the reverse of t and the reverse of what? X column s prime, and this is equal to s, right? So this is s. X column s prime is s. So the reverse s. So we are done, right? So again, we had this, we said, so in conclusion, since this holds by induction so this holds for S, for any S, and since we took arbitrary t, then it holds for any S and for any t, okay? But then, look, we had this, we just had to make some induction on S, so we said let S be an empty string, we just put the value of S here, and we obtain that it holds. And now we assume that this property holds for some S prime. And so we want to show that it holds for S if S is equal to X column S prime, right? And then all we have to do is write this into this formula, and we need to obtain this somehow using the definitions or using some lemma we already know. And that's it. So that's all we did. We put this into this, and we obtain that this is true. And that's it, okay? For 16a, this was A, I think. Yes, A. Now B. So 16b. We have to prove that for all S, so that for any string holds that the reverse function of the reverse function of S is equal to S. And this is clear. So if we take any, I don't know, let S be again 1, 2, 3. The reverse is going to be, so S, the reverse of S is going to be 3, 2, 1. And the reverse of the reverse is going to be 1, 2, 3. So this is true. This is quite clear. But anyway, we need to prove it. Okay? So how are we going to prove this? What do we need to do? No, I told you don't talk about elements here. So S is what have we done before to prove anything? How we proved? By induction. So every time you have something like this, you have to do it by induction. That's 100%. Well, not 100%, but almost sure. Okay, so by induction on S. Just by induction. Okay. Yes, so the base step, you are thinking about strings as sets. These are not sets, okay? We are going to study sets, but I don't know when, like in 1 month, okay? But these are not sets, okay? These are sets, but don't think about it like sets, okay? Because, for example, in one set, so if you have this, for example, this is not equal to 1, 3, and 2, okay? But if we say that we have a set of 1, 2, and 3, so this is equal to this in one set. But if this is string, so this is not equal, okay? Because the order here matters, and the order in a set doesn't matter, okay? So, base step, we have to assume that S is an empty string, then the reverse of an empty string is equal to what? What is this equal to? The reverse of an empty string. Empty string, right? By definition. So by definition, this is empty string. And then we obtain the reverse of an empty string. And again, by definition, this is the empty string. Check. Okay. So we took that the reverse of S, which is an empty string, is F. Now, the inductive step. So again, S is equal to what? Yes, X column S prime. And we assume that this property holds for S prime, right? So we need to put this into the equation. So we need to put this here. So the reverse of X column S prime is equal to what? So look at this. What is this equals to? So we have to go here to the definition and look, the reverse of X column S, the reverse of X column S prime. So this is equal to the app, so the reverse of the app of the reverse of S and X, right? S prime, yes. Thank you. Now, what can we see from here? What do you think? So we have the app of the reverse and some X. So, any idea? No? What we proved, what we just proved, we proved that this is equal to this. So we have the reverse of the app SG and this is the reverse of the app, yeah, and this is the reverse of the app some ST, right? So this is equal to what? So look, this is the same as this. This is for the last from the last exercise. So in the last exercise, we proved that this is equal to this. Now we can apply this here. So we can apply and we say by problem, this was 16a, this will be equal to, so let's erase this. So wait. So this is going to be equal by this exercise to the up of the reverse of t, in this case t is x, right? And the reverse of s, and s in this case is the reverse of s prime, right? Yes? And then what is this equal to? What can we see here that maybe is good for us? So what is this equal to? The reverse of s prime. What did we assume? So this will be s prime, right? So this is equal to s prime by, so then let's write here, by the inductive hypothesis. Right. This is equal to the up of the reverse of x and s prime. Yes? And now the reverse of x is just x as well. Is x, so we have x, which is going to be x. So this is equal to the up of x, string s, and s prime. And what is this equal to? The up of x and s prime? Again, please, what? So, what is this? Yeah, so this is s. Right? Because x and s prime, so s. And that's it. So we obtain that. What you would say that for s, this is s here. The reverse of s is equal to s. And then the proof is finished. Okay. So this could be a bit long, but you just don't need to get confused for in any step here. But it's not very difficult. And that's it. So we are done with problem set number 1, finally. Now let's move to problem set 2. This problem set is already in the Google folder, in the Google Drive. So you can download anytime you want, right now if you want, if you're in your house, in your home. So what's the following? So we finish with strings. What's the following thing we need to study? What did you study yesterday in your lecture? What? Which one? Yeah, but which lemmas are this? Yeah, lemma 1 is any lemma can be lemma 1. What is the statement of the lemma? Huh? Okay, so no. And on YouTube, does somebody remember? Okay, let me remind you. So you talk about induction for natural numbers. Yes? Now you remember? Yes. Good. So what is the set of the natural numbers? So we still don't know what a set is and everything, but by intuition we know that. So the natural numbers are this from 0, 1, 2, and so on. Okay. These are the natural numbers, and then we can't translate the we can translate induction on strings into induction for natural numbers. Actually, induction for natural numbers is going to be like a special case of the induction on strings, and you will see that in your lecture. Okay, and we define the MIP. What is the meaning of this? Mathematical, right? The mathematical induction principle. So the mathematical induction principle, but this is not the only one you defined. You defined another one called where's the name of that? LMP. The least number principle. So we have two different tools, two different ways of applying induction. And which one are we going to apply? It depends on the problem, on the exercise, of course. So we have the mathematical induction principle and the least number principle. What? Okay, let me write them just MIP. So MIP. So we say that for all unary predicate phi over the set of the natural numbers, if phi of 0 holds and for all n, so for all natural number, if 5 of n holds, if 5 of n holds and 5 implies that 5 of n plus 1 holds, then for all n, phi of n holds. So this is the mathematical induction principle. If we have some predicate, unary predicate, and if it holds for 0, and if from assuming that for any n natural end, phi of n holds, this implies that phi of n plus 1 holds, then phi of 5 of n holds for any n, for any natural number, okay? And this is a very strong, very powerful tool that is used in number theory, like in all the course of number theory. So, and we're going to use it here to resolve some problems. What problems? Okay, well, let's start. I think we can resolve a couple of problems today on induction. These are really nice. We'll see. So Okay, so this is class work 2, exercise number 1, I think. We have to prove, so prove that for each natural n at least that is at least one, the following hold. A, the sum from k1 to n of 2k minus 1 is equal to n squared. This is 2, okay? So we have to prove, by the way, do you know what is the meaning of this? Yes? No? Yes. So does everyone know? Because, I mean, I'm sure that not everyone knows. So this is that we have to put the value of k in each of these cases, right? So for k1, so this is equal to, so for k1 will be 2 minus 1, yes, so 2 multiplied by 1 minus 1 plus k2, so we have to do it now for k2, so 2 multiplied by 2 minus 1 plus 2 multiplied by 3 minus 1 plus so on until n, so plus 2n minus 1. So this represents this sum, okay? But we don't write this because it's not very nice to write it, okay? So, and you are going to see this everywhere, and then we are going to see integrals and so on. Anyway, it doesn't matter now, so good, you know this. Well, how are we going to prove it? I think you should know how to prove this, because in your lecture yesterday you did something like this. I don't remember. You proved in your lecture, you proved that the sum, so that 1 plus 2 plus 3 plus 4 plus so on plus n is equal to what? N plus 1 or 2, yes. So you proved this in your lecture, right? And this is going to be exactly the same as you did in your lecture. So we can prove not only this, we can prove this, for example, 1 squared plus 2 squared plus 3 squared and so on. And anything you want, we can prove it this way. So what do we need to do here? How are we going to prove it? Of course, yeah, of course by induction, first of all, of course, because this is, we're talking about induction, so it has to be by induction. So by induction, on what? Yeah. Yes, but yeah, that's when we apply induction. But I'm telling you, I'm asking you just, we have to prove this by induction on what? So every time you say I'm going to prove this by induction, you have to say on what? Induction, it means that you say that something is equal to 0, and this something then is equal to anything. This something should be written here. So this is by induction on n. Do you understand? So n is going to be, it's going to change their value. So we need to prove this for n 0, as you said, and then for any n. Okay. So if the first thing, so you can write just by induction, but you have to understand by induction on what? On n in this case. Okay. So what do I need to write? What's the first thing I need to do? Yeah, so the base, the base step. So I need to check this, if this is true, right? So this is going to be phi, okay? And I need to check that for n0, this holds. So I need to check, well, actually, it's going to be that for n, yes, so this is going to be phi. I need to check this, right? Look, this is important. This is very important. Do not forget about this condition here, okay? So that if n is at least 1, then this holds, okay? So we need to check this for 0. So we need to check that yes, so we just the sum of k1 to 0 of 2k minus 1 is equal to 0, right? So I need to check that this holds, for n0. So what can I say from here? What is false? Yes, this is true. Why? Yes, so this is false. Then this is true. So we checked the base step. Okay, so phi of 0 holds. Now we have to check for other values of m. So, inductive step. So we already checked the base step. Now I have to check the inductive step. So I assume that I have to check that for all n, if f of n holds, then f of phi of n plus 1 holds. Okay, I have to check this. So this is true. I'm going to assume that this is true, and then I need to obtain that this is true. Okay, so let me write that in a more formal way. So assume that for n natural, phi of n holds. So that for n at least 1, the sum of k1 to n of 2k minus 1 is equal to n squared. So we assume this. We assume that this is true, that this holds. Okay, and I need to check this, right? So I need to check that for n plus 1, at least 1 holds that the sum k1 to n plus 1 2k minus 1 equal n minus 1 n plus 1 square. So I assume that this is true, and I want to check that this is going to be true as well. Okay. So notice that here we have n, 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 and here we have n plus 1, n plus 1, and n plus 1, and n plus 1. This is important. Okay. So we have two cases. First case. What if n is equal to 0? In this way, in this case, can we apply the inductive hypothesis? No, look. So we have to check this, you know. So I have to check this for all possible n, for all n, and then I say that if n is natural, n then can be 0, right? But if n is 0, can I apply this? No, because to apply this, I need this to be true, and n is less than 1. So I cannot apply the inductive hypothesis right now. What can I do? I just can put this value here. Okay, and so there, and I obtain the following. So I obtain here, so from k1 to 1, right? So this, put it here, but for n0, I have to check that for n0 this holds. So for n0, this is true, yes, and I have to check if this is true. So this is the sum from 1 to 1 of 2k1. So this is going to be 2 minus 1, so 1, equal to 1 squared, so 1, right? 1 equals 1, so this is checked. Yeah. So this holds for n equals 0. Now we have to check the second case. For n at least 1. And now we can apply the inductive hypothesis, right? So do not forget about this step. You have to do it, because if you from the beginning say no, that we need this, so we apply inductive hypothesis and everything holds. Well, this is not true because you haven't proved it for n equals 0.
But in number theory, we should do the same, or is it
I don't know what in number theory. I mean, what do you mean? Like
it's because in number theory,
you
just 3 steps, like the 3 steps, the basic, the induction. No.
well,
No, I think it's the same.
yeah, I think it's the same because there are, I don't know, for example, in calculus or in maybe it's yeah, it has not to be that formal sometimes, but anyway, it's good to do it that way. Okay, so in this case we can apply, let's apply the inductive hypothesis. Okay, so then let me erase this. Okay. Then, okay, what do I need to write? What do I need to do? I know that I can apply the inductive hypothesis. So good. What do I need to write here? Yeah, so yeah, for this case, this we can apply it. So let's find that this is true. So what? So we need to find that this holds, right? So I need to write this and see if this is equal to this, right? So this is the sum from k1 to n plus 1 to k minus 1. And now what? Mm-hmm. Plus what? Yes, so 2 n plus 1 minus 1, right? Mm-hmm. And now this is equal to what? So this is equal to, yeah, n squared, right? So this is n squared plus 2n, okay, 2n plus 2 minus 1. And this is equal to what? So this is n squared plus 2n plus 1 that we can write just like n plus 1 squared, right? You should know this. I mean, so this is equal to this. So it holds, it's true. Okay, I forgot to write here just by induction hypothesis. And then to finish with this, so let me write, so we obtained that phi n plus 1 holds. Then by the mathematical inductive principle, for all n, phi of n holds, and the proof is finished. So that's it for today. I will be waiting for you in Zoom tomorrow at 6 o'clock.